Hi, my name is Prakash. I'm a PhD student at IIT Bombay. Our paper is titled Best Time Identification in Sample Path Correlated Bandits. And this is a joint work with Professor Nikhil Karamchandani and Saryu Mohrir. This problem is motivated by software as a service applications like video on demand services, online shopping platforms, etc. Many software as a service offers a range of versions to their customers, where the more expensive versions provide better quality of service to the customers. For example, Netflix offers multiple versions to customers for subscription. The cost of each version is known, whereas the reward accrued from the version is difficult to predict without trying it out. We define the utility of each version as the difference between the reward accrued by the customer and the cost of the version. Identifying the version which provides the right balance between the two is an important problem. This motivates the learning problem of identifying best version of the service efficiently. We map this problem to widely studied best term identification problem with some additional structure. We refer K versions as K arms of the multi-arm bandit. The cost of pulling an arm I is denoted by Ci, which is a known quantity. Without loss of generality, we assume that arms are indexed in the increasing order of cost. Further, the reward is obtained by pulling arm I is modeled as Bernoulli random variable with parameter Ri, where Ri's are unknown. Let RIT denote the reward of arm I in round T. We consider the setting where an arm with higher cost has higher reward than an arm with lower across sample path. Therefore, for our setting, I greater than j implies cost of arm I is larger than cost of arm j, and which implies sample reward of arm I is greater than sample reward of arm j in round T, which further implies mean reward of arm I is greater than mean reward of arm j. To better understand the sample path correlation, let us look at the example. Let us consider there are 8 arms and reward of arm 5 is revealed to us as 0. Then, by using sample path correlation, we can infer rewards of arms 1 to 4 as 0. Similarly, if we observe 1 as reward for arm 5, then we can infer reward of arms 6 to 8 as 1 using sample path correlation. We now continue with our problem description. The mean utility of arm I, mu I, is defined as the difference between the reward of arm I and the cost of pulling arm I. The best arm is defined as the arm with highest mean utility. The goal is to identify the best arm under fixed confidence setting. That is, given delta greater than 0, we need to identify the best arm with probability at least 1 minus delta. The algorithmic challenge is to determine which arms to sample to identify the best arm. The performance metric is the number of samples needed to identify the best arm correctly with probability at least 1 minus delta. We consider 2 types of feedback models in this work. First is the full information feedback model, in which reward of every arm is known in each round. And the goal is to identify the best arm in the minimum number of rounds with high probability. Second is the sequential feedback model. Under this model, in each round, we sample specific arms sequentially. Only the reward of the arms that are pulled in a round are revealed, and the reward of all other arms in that round remain unknown. The best arm identification problem has been widely studied. In most basic version of the problem, utilities are independent across arms. The best arm identification problem with correlation across arms has also been studied. In this work by Gupta et al., it is assumed that upper bound on conditional utility of an arm given utility of another arm is known. The others show that this structure can be used to identify the best arm using fewer samples. Our problem setting is different from the one considered by Gupta et al. In our setting, utility is defined as the difference between the reward and the cost. Cost of arms are known and the rewards are sample path correlated across arms. The key question is, can sample path correlation be exploited to improve performance? Before we proceed further, we need to understand the concept of confidence interval and upper and lower confidence bounds, that is UCB and LCBs. Let mu be the mean utility of an arm, and mu hat n represents the mean empirical utility of an arm after n samples. The confidence interval represents the interval in which mu lies with probability 1 minus delta. Typically, the concentration inequalities like Houbling's inequality is used to characterize the confidence interval. As the number of samples increase, the confidence interval shrinks. Recall that we consider two information models. We will first present our results for the full information setting. Here, in each round, we obtain samples of all arms. Our policy for full information feedback is as follows. In each round, we use the samples to update empirical means, LCVs, and UCVs of all arms. We eliminate an arm if UCV of all arms, UCV of the arm is less than LCV of any other arm. It is therefore sufficient to compare UCV of an arm with the highest LCV across arms. Once an arm is eliminated, it is not to be considered in any further rounds. Here we can see arm 2, 3, 4, 8 are eliminated and they are not considered any further. Once we left with only one arm, we will output that arm as the best arm. Our first analytical result is an upper bound on number of samples needed for our algorithm. We see that upper bound scales as log k by delta square, where k is number of arms. Our next analytical result provides a lower bound on expected number of samples needed by any policy, any online policy. We see that the lower bound scales as 1 by delta square. We thus note that our policy is suboptimal by at most log k factor, and it has order optimal performance with respect to confidence parameter delta. We now move to the sequential feedback setting where only the reward of the sample arms are revealed. The key idea behind our algorithm for this setting is to mimic our algorithm for the full information setting. Thus, we infer the rewards of all arms in each round. The naive approach is to do this. Is to sample all the k arms sequentially to infer the full reward vector. Our approach is to exploit sample path correlation. Recall that higher index arms has higher reward in sample path. Let us consider the setting where we have 8 arms. We first pull arm 4, which is in the middle arm. Based on what we observe, we infer the reward for other arms. We repeat this process until we infer the reward of all arms. Under this approach, which mimics binary search, we need at most log k base 2 samples in a round to infer the entire reward vector. Our policy is also known as adaptive policy. We first get the samples of all arms by using binary search approach discussed before. We then follow the same procedure as full information setting to eliminate arms. I will now present our analytical results for sequential information setting. We characterize the upper bound on number of samples needed under our policy. Note that the bound scales as log k to the power 2, where k is the number of arms. The key ideas used in the proof are to characterize the number of rounds needed to eliminate each suboptimal arm and exploit the fact that eliminating arms reduce samples needed in the future rounds. Here is a summary of our analytical results. We note that sample complexity under our policies for both settings scales polylogarithmic and is at most polylog factor away from optimal. We now present some simulation results. We choose the following policies from existing literature to compare with our policy via simulations. Adopt please our policy for sequential information setting. LUCB pulls 2 arms in each round. CLUCB is a variant of LUCB which exploits correlation across arms. Act2P algorithm pulls all active arms in each round, whereas active arms are those arms which are not eliminated. Arm I is characterized by rho I, which lies in the interval 0 and 1. The cost of arm I is C rho I, where C is a constant. We consider 2 types of reward functions. One is synthetic and the other was obtained from the data set in the footnote. We choose arms almost uniformly in the interval 0 to 1. For this set of results, we consider synthetic reward function. We vary cost of pulling an arm and compare the performance of various policies. We observe that our policy performs better than other policies. We next consider the data-driven parameter functions. We compare performance of our policy with others and observe that our policy performs better than other policies. To conclude, we introduce a variant of the sum identification problem for multi-arm bandits by introducing sample path correlation. We propose near optimal policies which exploit this correlation. Simulations show that our policy outperforms other policies which do not take sample path correlation into account when making decisions. Thank you.